Hi, welcome to the next video. This is a review of 3.7 and chapter 4. Okay, so refer to the textbook during this lesson. Okay, so take your textbooks out so that you can follow along with this lesson. If you don't have it, maybe pause the video and get the textbook. Okay, so first let's start out at 3.7. Okay. So follow along with me in the book. So right in page 189 in the book textbook, 3.7 antiderivatives. Okay, so there's the definition of an antiderivative, right? A function capital F is called an antiderivative of f on interval I if capital F prime of x equals little f of x for all x and I. So you need to know what an antiderivative is, right? Okay. Right, so for instance, capital F of x equals sine x is an antiderivative of little f of x equals cosine x. And why is that? Because capital F prime of x is equal to cosine x, right? If you were to take capital F prime of x, it would be the derivative of cosine, of sine, which is cosine, right? This is a function whose derivative is little f. And so capital F is an antiderivative of little f, okay? That's an example. Okay? Right? So if capital F is an antiderivative of little f, right? So if capital F is an antiderivative of little f, then the most general antiderivative is capital F of x plus an arbitrary constant c, right? So if you add a constant, any constant to an antiderivative, you have another antiderivative. And so these are all antiderivatives of little f. They're also all of the antiderivatives of little f, okay? So this is the most general, it's called the most general antiderivative of little f, okay? And so that's an introduction to 3.7. That's the beginning of 3.7, okay? And so you need to know how to find the most general antiderivative of functions. Okay? Okay. Okay, so right at the bottom of page 190 in the textbook, there's a table of anti-differentiation formulas. So you should look at the table at the bottom of page 190, and you should know that table. Okay? Okay. So it's a brief summary of 3.7. Okay. The next section is, now we go to chapter 4, and it starts with 4.1, areas and distances. Okay. So for chapter 4 is about integrals. Okay. And so you use the definite integral to find areas. Okay. And so in chapter 4 we discuss integrals. And 4.1 is on areas and distances. Okay, and so let's first look at on page 204. There's definition 2. Okay, and so the area capital A of the region S that lies under the graph of the continuous function f. And so let's say you have an x-axis here, you have a y-axis here. Let's say you have a continuous function f here. Okay, let's say it's defined from A to B here. Okay, so this f is defined on this interval. Okay, then the area A of the region underneath the curve, right? A is the area of this shaded region. The area A of that shaded region, capital A, according to definition 2, is the limit as n approaches infinity of f of x sub 1 delta x plus f of x sub 2 delta x plus dot 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 plus f of x sub n delta x. Okay? And so this is x naught, this is xn. And so if you split this up into equal subintervals, going from x naught to xn, okay? And so the x sub I here is a plus I delta x, where delta x is b minus a over n. Okay, and so that formula is how you find the area underneath a continuous curve, right? And so, and so there are problems where you have to use this limit definition to find the definite integral. And so you need to know that. Okay, so that's 4.1, brief overview. Okay, in 4.2, so in 4.2, we start formulating the definite integral. Okay, and on page 213, Theorem 4, so in page 212, definition 2 is the definition of a definite integral. And so technically, the definition of the definite integral involves this formula, okay? And so this is the definition of the definite integral along with the conditions of it, right? But I will not require you to use this to get an answer to any problem, okay? So you will not need to use this definition for the first exam for this exam to get an answer, okay? That's if the limit exists, okay? So in definition 2 on page 212, they give you this equation, okay? And so this is the definition of the definite integral. But instead of using this, you can use the simpler one, which is on the next page, page 213, and it's Theorem 4. And so it says if f is integrable on the finite closed interval a comma b, then the definite integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x, where x sub I is a plus I delta x, and delta x is equal to b minus a over n. Okay, and so Theorem 4, page 213, Theorem 4, you should know how to use this to calculate the definite integral. So having a definite integral like this, you should be able to find the value of it using that limit definition. Okay. Okay, and so you need to know the properties of summations in order to calculate that limit. So you'll need properties of the summation of the Riemann sum to do that. You also need to know these formulas. Okay, the sum from I equals 1 to n of 1 is n. That's easy. The sum from I equals 1 to n of I is n times n plus 1 over 2. It's a little bit harder. Okay, the next one, the sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 divided by 6. That's a little bit more difficult. That's probably the most difficult one. Okay. And then the fourth one you need to know is the sum from I equals 1 to n of I cubed is n times n plus 1 over 2, that entire fraction squared. Okay, and so you need to know those 4 summation formulas because when you're confining this limit, you'll need to use these. In different problems, you need to use these 4. Okay, so make sure you know these 4 equations in addition to Theorem 4 on page 213. Theorem 4 on page 213. Okay, and you need to know these 4 also. This comes up a little later, but I'm just going to bring it up now because this is where the summation is first brought up. Okay? Okay. So you need to know that. Right? You need to be able to estimate the value of the definite integral using left endpoints, using right endpoints, and using midpoints. Okay? So you need to be able to use left endpoints, right endpoints, and midpoints to approximate a definite interval or an area. Okay? Starting on page 218, in the textbook. You have properties of the integral. And so the list continues to page 220. There's 8 properties. So you need to know those 8 properties. Okay. Okay, and so that's 4.2. Okay, 4.3. 4.3, they introduced the evaluation theorem. Okay, and so the evaluation theorem says if f is continuous on an interval a comma b, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f, that is capital F prime equals little f, where capital F prime equals little f. Okay, so that's the evaluation theorem. That's also part of the fundamental theorem of calculus. So for instance, if you have the definite integral from 1 to 2 of x dx, right? This x is little f, right? So little f is x. Now we need an antiderivative of that function. So let's say capital F of x is 1/2 x squared. Okay? The derivative of 1/2 x squared is x. So capital F is an antiderivative of little f. And so you just take this function capital F, and by the evaluation theorem, this is capital F of 2 minus capital F of 1. And note, the other way to write this is capital F of x evaluated from 1 to 2. This notation is just saying it's capital F of 2 minus capital F of 1. That's what this notation is. So I frequently use this notation in the lessons, right? And so I prefer this because it's shorter than writing this. Using this notation means you write less. And so anyway, the value of that, you plug in 2 into here. You get 1/2 times 2 squared minus, plug 1 in to that capital F, and get minus 1/2 times 1 squared. So that's equal to 1/2 times 4, which is 2, minus 1/2 times 1, which is 1/2. And so your answer is 3/2. So now we've calculated this definite integral. It's 3/2 using the evaluation theorem. Before, up to this point, you only have the limit definition, and so you'd have to calculate a limit which would take up the entire page, writing very small. Here, using this evaluation theorem, you can get the answer very quickly. Okay? And so the book, there's a proof of the evaluation theorem in the book, and you can read it if you want. And so with this theorem being proved, you can use it, and it makes calculating a lot of definite integrals very quick and easy. Okay? So this doesn't solve our problems entirely, because you can't always find an antiderivative easily, right? And so you need to build on you need more than the evaluation theorem, because there are other definite integrals where this is not enough. You need other things. But we get to that. Okay, so continuing. So that's calculating a definite integral, because there's lower and upper limit. That's a definite integral. Okay, and a definite integral will represent an area under a curve. Okay, there's also what's something called an indefinite integral. And so if you have an indefinite integral, right, this is the indefinite integral of the function little f. And so that equals capital F of x, means capital F of x prime is equal to little f of x. Okay? Okay, so the indefinite integral is a function, or a family of functions. So the indefinite integral is a family of functions, all whose derivative is this function. So an antiderivative is a function. A derivative, a definite integral is a number. So right, for instance, definite from 1 to 2 of x dx, remember we got was 3/2. And so a definite integral will give you a number. An indefinite integral will give you a function. Okay? Okay, a definite integral gives you the area under a curve, and it's a number. An indefinite integral will give you a function whose derivative is that function. Okay? So there's a difference between the two. Okay? And at the bottom of page 226, there's a table of indefinite integrals. Okay, so on the bottom of page 226 is a table of indefinite integrals. Okay. Okay, so then, so we continue. That's a short summary of 4.3. Now, when you go to 4.4, that starts on page 233, it talks about the fundamental theorem of calculus. Okay, if you read the book, that could help you too. Okay, so, and so it tells you about the fundamental theorem of calculus, and there's two parts. So part 1 is on page 235, and parts 1 and 2 are on page 237. Okay, so we have the fundamental theorem of calculus. Okay, there's a formula for the average value of a function on page 238. It tells you the average value of a function on an interval a comma b is 1 over b minus a times the differential from a to b of low f of x dx. Okay, so that's if this is the average value of a function on a finite closed interval a comma b. Okay, we have the mean value theorem for integrals on page 239. Okay, you can look at that also. Okay, and then we go to 4.5. Okay, and so 4.5, the last section here for this video, is on the substitution rule. Okay, and so I went over the substitution rule in the lesson, but we'll do some problems in a little bit, and so we'll be using it, and that will help. And also page 245 is the substitution rule for definite integrals. Okay, you use the substitution rule for indefinite integrals and for definite integrals. Okay, so that's something important. And on page 246 is integrals of symmetric functions, and so it's relationships with even and odd functions f. Okay, and so that's a brief overview of 3.7 in chapter 4. Okay, now if you go to the chapter 4 review, if you start on page 250 of the textbook, there are exercises afterwards at the end of the chapter. Okay, so now I'm just going to go over some exercises with you to review. Okay. Okay, so let's do that. That's I feel much more beneficial than reading over the textbook. Our exercises, and so on page 250, we're going to go from page 250 to 251. Okay, so we're looking at pages 250 and 251. Exercises. Okay, let's go to number 7. Okay, so let's start with number 7 on page 250. And it says evaluate the integral if it exists. So this is the definite integral from 1 to 2 of 8x cubed plus 3x squared dx. Okay, and so we're going to use the evaluation theorem for this. Okay, and to do that, we're going to find an antiderivative of the integrand function. And so what is an antiderivative of the integrand function? Well, you have 8 in front, then you have x to the 4th over 4 for the x cubed, plus 3 times x cubed over 3, plus, oh, not plus, okay. So here's an antiderivative of the integrand. And then you evaluate it from the lower limit to the upper limit of the integrand. Right? And so this is equal to 8 over 4, which is 2, 2x to the 4th, plus 3 over 3 is 1, so you get just plus x cubed, and that's evaluated from 1 to 2 still. And just plug in 2, and you get 2 times 2 to the 4th plus 2 cubed minus 2 times 1 to the 4th plus 1 cubed. Okay, so you calculate that and you get 32. 2 times 2 to the 4th is 2 to the 4th is 16. 16 times 2 is 32. 32 plus 8 is 40. So that's 40 minus 2 plus 1 is 3. And so you get 37. And so that definite integral is equal to 37. Okay, so that's exercise 7. We use the evaluation theorem here. Okay, so this is a good practice for the evaluation theorem. continue. Let's do another evaluation theorem problem. So let's do number 10. Now here's number 10. Number 10 is the definite integral from 0 to 1 of 1 minus x to the 9th power dx. And so first, your very first thought is, okay, maybe you get the evaluation theorem, and maybe that's easy, right? But then it's 1 minus x to the 9th power. And so your first thought is, well, if I multiply 1 minus x by itself 9 times and write it out, then I can find an antiderivative, and I can use the evaluation theorem. I can get the answer. It's a lot of work, but I can get the answer, right? And so you can get the answer by multiplying 1 minus x by itself 9 times, adding common terms, and then using the evaluation theorem. But an easier way is just to use substitution. Okay, so let u equal 1 minus x. Du is equal to negative dx. Okay, well, negative dx is also negative 1 dx, so I'm going to put negative 1 there. So here, in order to substitute for du, I need a negative 1 dx, but I'm missing it. I'm missing a negative 1 here, so I'm going to remedy that by adding a negative 1 there, by putting a negative 1 there. So now I put a negative 1 there, right? But by putting a negative 1 there, I'm now saying this is equal to the negative of itself, which is false, right? I can't just take the negation of something and say they're equal. But I can fix that by multiplying it by negative 1 again. If I take a number, which that is, a definite integral is a number. If I take a number and I multiply it by negative 1 twice, then it stays the same. And so I multiply by negative 1 here because I need a negative 1 to use substitution. And then multiply the outside of the definite integral by negative 1 again. And so I can say that these two things are equal. Now, I have negative 1 times the definite integral. I'm going to leave the limits for later. U is 1 minus x. So what's in the parentheses here is u. And I'm raising u to the 9th power. I wrote the parentheses just so you can see that that's u. Now this is negative 1 dx. Negative 1 dx is du. And so now I'm going to substitute du there for this. Now I'm using the substitution rule for definite integrals. And so in addition to just replacing x's here with u's, I need to replace these x values with u values. And so when x is 0, 1 minus 0 is 1, and so u is 1. And when x is 1, 1 minus 1 is 0, and so u is 0. And so now with this equal sign, I've said this is equal to this using the substitution rule for definite integrals. Okay? And so now I can also say, using properties of definite integrals, I can switch the order of the limits of integration. I can switch them. But then I just have to negate it. But if I negate this, it's already negative of it. And so if I negate the negative sign is here. All right? And so now you just calculate that definite integral. And so what that's equal to, an antiderivative of u to the 9 is u to the 10 over 10. And now I'm going to evaluate it from 0 to 1. Okay? And so that's equal to 1 to the 10th over 10 minus 0 to the 10th over 10. This is using the evaluation theorem, and this is just finding the value of that expression. That's 1/10 minus 0. That's equal to 1/10. So the final answer is that definite integral equals to 1/10. And even though this took some work using the substitution rule for definite integrals, it's less work than multiplying 1 minus x 9 times, combining like terms, and then using the evaluation theorem. So this is faster than the other way to do it. All right? And so this is number 10. So sometimes there's more than one way to calculate an indefinite integral, but there is a faster one. This is the faster route. Okay, so let's go to another problem. Okay, so now we've seen 2 examples in this lesson of calculating a definite integral. The first one used the evaluation theorem. Well, they both use the evaluation theorem, but this one also used the substitution rule. Okay, here's another definite integral, number 11. Okay, we're going to evaluate this definite integral also. It's a definite integral from 1 to 9 of the square root of u minus 2u squared divided by u du. Okay? So first thing we'll do is I'm going to rewrite this using exponents, using an exponent. So this is the definite integral from 1 to 9 of u to the 1/2 minus 2u squared over u du. And now, this is a one fraction. I'm going to separate them into two fractions. So this is the definite integral from 1 to 9 of u to the 1/2 over du to the first. That's u to the 1/2 over u to the first. You don't have to write all these steps, but I'm writing them so you can follow. Minus definite integral from 1 to 9 of 2u squared over u du. Okay, so I just wrote this one fraction as a difference of two fractions. Right, because if you have a minus b over c, that's a over c minus b over c. Kind of like that. A minus b over c is a over c minus b over c with the integral sign, with the definite integral involved. Okay, and so now this is equal to u to the 1/2 divided by u to the first is u to the 1/2 minus 1. That's u to the negative 1/2 du. Minus definite integral from 1 to 9. 2u squared over u is 2u du. Okay, so now let's calculate each definite integral. And so this one is find an antiderivative of that. That's u to the 1/2. Add 1 to the exponent, you get 1/2. Divide by the new exponent. Okay, evaluated from 1 to 9. Minus, find an antiderivative of this, which is u squared. And evaluate it again from 1 to 9. Okay, this is using the evaluation theorem twice. This is equal to, this is 2u to the 1/2. So let me write that here. Dividing by 1/2, right? And I've showed you that is now 2u to the 1/2. Okay, so you get 2 times the square root of 9 minus 2 times the square root of 1. Raising something to the 1/2 is the square root. So u to the 1/2 is the square root, right? Same we did it the other way around before. Okay, so this is 2 times the square root of 9 minus 2 times the square root of 1. That's this guy. Minus this. So this is minus 9 squared minus 1 squared. And so this is equal to square root of 9 is 3, square root of 1 is 1. 2 times 3 is 6. 6 minus 2 times 1, which is 2. 6 minus 2 minus 9 squared, 81 minus 1. This is equal to 4 minus 80, which is negative 76. So the answer is negative 76. All right, and so you can have a differential be a negative number because area is signed. What's above the x-axis is positive, what's below the x-axis is negative. Okay, so that's number 11. Okay, let me check the camera. Good. Let me check one more time. That's good. Okay. So, next, continuing. Let's do number 14. Okay, so number 14 is the definite integral from 0 to 2 of y squared times the square root of 1 plus y cubed dy. Okay, so we're going to use u substitution here. And so first thing you ask is what should you let u be? So I'll give you a moment to think about what u should be there. Usually it's the weirdest thing, right? But u should also be something simple. It should be something simple, but something that is making that complicated. Okay, so let u be what's inside the square root. Let u be 1 plus y cubed. Let u equal 1 plus y cubed. Some people's first thought might be to let u equal the square root of 1 plus y cubed. Don't do that. Simply, just 1 plus y cubed. So let u equal 1 plus y cubed. Du is 3y squared dy. Okay, and so now we just need to substitute. I can put a u in the square root, and I have a y squared dy. So I'm missing the 3, so let's fix that. We have the definite from 0 to 2. I'm going to rearrange the terms. The square root of 1 plus y cubed. And then I have the y squared dy here. I'm missing a 3, so I put a 3 there, and I put a 1/3 on the outside. I multiply by 3 and by 1/3, which means it's still equal. Okay? This is equal to 1/3, definite integral, the square root of u, because that's u, right? And that's u here. That's u. And then this, the 3y squared dy, is du. And so that's du. See? This is the square root of u, du. And then we find the corresponding values of u here and here. So when y is 0, 1 plus 0 cubed is 1. When y is 2, 1 plus 2 cubed is 1 plus 8, which is 9. U is 9. Okay? Writing using exponents, this is the same as the 1/3 definite integral from 1 to 9 of u to the 1/2 du. Okay? Well, now this is equal to, what's an antiderivative of u to the 1/2? It's u to the 3/2, adding 1 to the exponent here. 1/2 plus 1 is 3/2. Then dividing by the new exponent, 3/2. But dividing by a fraction is the same as multiplying by its reciprocal. And so dividing by 3/2 is the same as multiplying by 2/3. And so an antiderivative is 2/3 u to 3/2. Okay, that's an antiderivative of u to the 1/2. But we have the 1/3 already. So this is 1/3 times the 2/3 u to 3/2. And we're evaluating it from 1 to 9. I'm going to move the constants out. This is 2 9s times 9 to the 3/2 minus 1 to the 3/2. Okay, and so this is equal to 2 9s times 9 to the 3/2, which is the square, the 2 in the denominator means take that, the root, the second root of that, the square root of 9, which is 3. And then this in the numerator means cube it. So the square root is for the 2, cubing is for the 3. So the square root of 9 is 3. 3 cubed is 27. 27 minus 1 is 26. The square root of 1 is 1. 1 cubed is 1. So 1 3/2 is 1. So you get 27 minus 1 is 26. Okay, and so now this is 2 9s times 26, which is 52 over 9. Okay, that fraction's in simplest form. Okay, 52 is 2 squared times 13, and that's 3 squared. They don't share any common prime factors, so this is in simplest form. Okay, so this is equal to 52 over 9. So that definite integral is 52 over 9. Okay, so this is number 14, and we use u substitution for this definite integral also. All right. Okay, so this is good practice for computing definite integrals, using the evaluation theorem, using u substitution. Now, let's do number 20. So for number 20, it's the integral of cosecant squared of 3t dt. Okay, so we're going to find find the most general antiderivative of this integrand function. So I'm going to use u substitution again because it's not cosecant squared of t, it's cosecant squared of 3t. So I'll let u be the 3t. So that's simple. Letting u equal 3t is a simple u. Du is equal to 3 dt. Okay, so I'm missing a 3 here. So this is equal to integral cosecant squared of 3t. And then the dt here, but I'm missing a 3. So I put the 3 there, and then I multiply the outside by 1/3. So multiplying by 3 and 1/3, the value stays the same. This is equal to 1/3 the integral of cosecant squared of 3t, which is u, and 3dt, which is du. Okay, so an antiderivative cosecant squared of u is negative cotangent u. So this is 1/3 times negative cotangent u plus c. Okay, so how do we know that? So the derivative, use x here. So we use x as for the formula, but we would just apply the formula where instead of using x, we use u. Okay, I'm going to use the formula x because that's how you see it. d dx of cotangent x is equal to negative cosecant squared x. Okay. Another way to think of it would be, this is the way you would think of the formula, d dx of cotangent x is negative cosecant squared x. Now, knowing that, you could also say that d dx of negative cotangent x is equal to cosecant squared x. Okay, so if the derivative of negative cotangent x is equal to cosecant squared x, then an antiderivative of cosecant squared x is negative cotangent x. And so here, an antiderivative of cosecant squared of u is negative cotangent u, and then plus c. So this is equal to negative 1/3 cotangent of u, which is 3t, plus c. That is the most general antiderivative of cosecant squared of 3t dt. Okay, so that's number 20. And so now here, now this involves trig functions, and not just sine, cosine, or even tan. This involves cosecant and cotangent. Okay. Okay, so now that I've mentioned the trig functions, the calculus students are always worried about the trig functions, and they're also worried about them in pre-calculus. So let me help you out a little bit here by reminding you about some derivatives. Okay, and so this is now math 142. So in math 141, you did derivatives, and so this is kind of review. Okay, so this is d dx of sine x is cosine x. d dx of cosine x is negative sine x. d dx of tan x is secant squared x. Okay, so this you can just remember. d dx of cosecant x is negative cosecant x cotangent x. And so you might be wondering why. We took the antiderivative before cosecant. That's why we got something. Now this is the derivative, which is that. d dx of secant x is secant x tan x. And d dx of cotangent x is negative cosecant squared x. Okay, so these are 6 derivative formulas that you should know. All right, and so from these formulas you get antiderivatives. Right, so the antiderivative of cosine x is sine x plus c. Antiderivative of sine x is negative cosine x plus c. And you can keep going, right? So like from this third equation, you would know that the integral of secant squared x dx is tan x plus c. So knowing those 6 equations means you can go in the opposite direction, say the integral of this is tan x plus c. Also, what we used in the last problem is that the integral of cosecant squared x dx is negative cotangent x plus c. Right, where there's a negative maybe in the other spot, right? So if you were to take d dx of negative cotangent x, you would get cosecant squared x. Right, okay? Right, so with these 6 derivative equations, you get corresponding antiderivative equations, or indefinite integral equations, okay? So you should know these 6 derivatives and the corresponding 6 integral equations. Okay, it's just 6 equations, and then you just go the opposite direction, right? So you're not memorizing 12 equations. You're kind of knowing 6, and then using them for the other 6. Okay, so that's a review of derivatives and antiderivatives of trig functions, and so I used that in the last example, example 20. Okay, let's look at number 19. It's going back one. This is another trig function question. It's a little bit harder, so this is good to do after. This is defined from 0 to pi over 8. of secant 2 theta, tan 2 theta, d theta. Okay, so you just saw the 6 derivative equations in the last board. Now you may not remember them, but maybe, or you could rewind the video. If you rewind the video now to those 6 derivative equations I just wrote, maybe you could look at this and see where we need to go with the problem. Okay, so in the 6 derivative equations, we have that the derivative d dx of secant x is secant x tan x. And so we'll be using this equation to find that antiderivative. Okay, but here it's just x. Here we have 2 theta, right? Here we have a variable, just a variable now. Now we have 2 times a variable here. And so we're going to use u substitution. We're going to let u be 2 theta. Let u equal 2 theta. Then du is 2 d theta. Okay, so now let's apply u substitution here. So this is equal to, I'm going to leave some space here. This is different from 0 to pi over 8 of secant 2 theta, tan 2 theta. And then instead of a d theta, you have a 2d theta. So I'm missing a 2, so I put a 2 there, and I multiply the outside by 1/2. Okay, now when you apply u substitution, this is equal to 1/2 times the definite integral of secant of u, tan of u, and then 2d theta, which is du. And so now I have this, that goes there. Now, when theta is 0, 2 times 0 is 0. And when theta is pi over 8, 2 times pi over 8 is pi over 4. And so now we have this 1/2 times this definite integral. We'll look at this derivative equation. The derivative of secant x is secant x tan x. If we use u, d du of secant u is secant u tan u. We want an antiderivative of secant u tan u. So it's just secant of u. See? It's just going the opposite direction. So if the derivative of secant x is secant x tan x, an antiderivative of secant x tan x is secant x. So we just use secant, we use the evaluation theorem, and we use secant u as an antiderivative of the integrated function. Okay, so we're going to use secant u here. And that was just from remembering the 6 equations. Okay, and so remembering 6 equations is not too difficult. Okay, so you remember 6 things. You remember lots of things all the time. You need to remember 6 equations. And then when you remember that one of the 6 equations, you see this, and an antiderivative of the integrand functions is secant u. Right? If you don't remember the 6 equations, then you're going to get stuck there. Right? But if you just know those 6 equations, an antiderivative of that is secant u. And so this is 1/2, because of the 1/2 there, secant u, evaluated from 0 to pi over 4, applying the evaluation theorem, this equal sign. And so this is equal to 1/2 times secant of u, which is secant of pi over 4, minus secant of 0. Okay? And so what's secant of pi over 4? Secant of pi over 4 is 1 over cosine of pi over 4. And cosine pi over 4 is root 2 over 2. Right? So you have to know how to evaluate trig functions. So that means that secant of pi over 4 is 2 over root 2. And secant of 0 is 1 over cosine 0, which is 1 over 1, which is 1. So secant of 0 is 1. So that's equal to 1/2 times secant of pi over 4, which is 2 over root 2, minus 1. And so 1/2 times that is 1 over root 2 minus 1/2. And if you simplify that, you get root 2 over 2 minus 1/2. That's root 2. This is a bunch of just simplification stuff. It's not adding really anything. This is root 2 minus 1 over 2 is 1 fraction, if you want to write that way. All right, and so that's the answer to number 19. And so now we've now computed another definite integral. This one uses u substitution and involves trig functions secant and tan. Okay, so this is another good example to go over. Okay, so now let's look at number 25. 25 is a definite integral from 0 to 3 of the absolute value of x squared minus 4 dx. Let's okay, so for this one, okay, this is a good problem. So for x squared, for the absolute value of x squared minus 4, right? Well, on the side here, x squared minus 4 equals 0 would mean that x squared equals 4, which means x equals plus or minus 2. Right? Now, we're only going from 0 to 3, so the minus 2 doesn't matter, right? So we're left with x equals 2. X equals 2 is the only x value from 0 to 3 where that's 0. And so if you look at the number line, if you go from x equals 0 to x equals 3, when x equals 2, the y value, x squared minus 4, is 0. When x is 2, the value of this expression is 0. When x is larger than 4, let's say you have 2.1, if you take 2.1 square and subtract 4, it's positive. If this is a little bit more than 1, when you square it and subtract 4, you get something positive. So all of these are positive. And then if you take a number between 0 and 2, where x is between 0 and 2, not equal to 2, and you square it and subtract 4, you're going to get something negative. Okay? So x squared minus 4 is 0 at x equals 2, positive greater than 2, and negative when it's less than 2. And so x squared minus 4 is equal to itself. The absolute value of x squared minus 4 is equal to itself if 2 is less than or equal to x less than or equal to 3. Because when it's 0, the absolute value of 0 is 0. And it's equal to the negative of itself, which is 4 minus x squared, if 0 is less than or equal to x strictly less than 2. And so here, it's negative. And so if you take the absolute value of something negative, you have to negate it to get its value. So the absolute value of x squared minus 4 is 4 minus x squared. It's the negative of x squared minus 4. Okay, so we now have a function for the absolute value of x squared minus 4. And so let's separate this in the interval from 0 to 3 into two subintervals, 0 to 2 and from 2 to 3. Okay? Well, if we're going from 0 to 2, then the absolute value of x squared minus 4 is 4 minus x squared. Okay, we're going to go from here to here. I'm jumping over this, okay? And so this expression, the absolute value of x squared minus 4, is 4 minus x squared from x equals 0, x equals 2. So this is the definite integral from 0 to 2 of 4 minus x squared dx plus the definite integral from 2 to 3. Now, the absolute value of x squared minus 4 from x equals 2 to x equals 3 is x squared minus 4. Okay, so this is just x squared minus 4. And so I did this to get rid of the absolute value sign. And so now you just calculate these two definite integrals that we normally would, and you add them, and you get that answer. The answer for that. So here, the antiderivative of this is 4x minus 1/3 x cubed, evaluated from 0 to 2, plus you have x cubed over 3 minus 4x, evaluated from 2 to 3. Okay? And so now you're applying the evaluation theorem to calculate both definite integrals. And so when you evaluate them, you'll get 8 minus 8/3. So I'm going to quickly calculate this. You plug in 2 there and you get 8 minus 8/3, and then minus 0. So the first thing is 8 minus 8/3, and plus, you plug in a 3 and you get 27 over 3, which is 9, minus 12. But that's minus, plugging in a 2, 8/3 minus 8. Okay, so 8, I'm hoping some things cancel here, and they don't. Okay, so we have 8 plus 9, this is a negative 3, 8 plus negative 3 is 5, 5 minus negative 8 is 13. I'm just going to calculate this. This is then negative 8/3 minus 8/3. That's minus 16/3. That's minus 5 1/3. That's 7 2/3. Okay, so this is 7 2/3. I wrote it as a mixed fraction. You could write it as one fraction or as three. Okay, that's 7 2/3. And so that's the value of that differential. So that's the answer to number 25. And that's a good one to see also. So let's continue. So we did quite a few examples on calculating definite integrals here, in addition to all the other stuff we did. Okay, so I think it's helpful to see the whole thing now. Let's look at number 30. So number 30 on page 251 is find the derivative of the function. So find the derivative of the function. So the function is g of x is equal to the differential from 1 to cosine x of the cubed root of 1 minus t squared dt. We want to find the derivative of it. And so applying the fundamental theorem of calculus, the derivative is just you plug in this function into there. So you get the cubed roots of 1 minus cosine x squared. I could have wrote cosine squared x, but I just want to emphasize what I'm doing here. Times the derivative of cosine x, which is negative sine x. Okay, then you multiply by the derivative of that, and you get that. Right? If this was just 1 to x, you would plug in x here, and then you would stop. Okay, so this is a special case. This is a little bit more complicated, this problem. So we went over it, and so you should know how to do that also. All right, so that's number 30. Let's continue. Okay, so next, let's do number 35. Okay, so we've been calculating definite integrals all this time. So for 35, it says use the midpoint rule with n equals 5 to approximate this definite integral. So it's definite integral from 0 to 1 of the square root of 1 plus x cubed dx. We're going to use n equals 5, and we're going to use the midpoint rule to approximate. Okay, and we're going to use the midpoint rule to approximate. So we're going to find an approximation for that definite integral. Well, n equals 5. So here's the subintegral from 0 to 1. We're going to separate into 5 subintervals. 1, 2, 3, 4, 5. And so if it's length 1, and you're separating to 5 equal subintervals, each one is length 1/5, or 0.2. 0.2, 0.4, 0.6, 0.8, and then 1. The midpoint rule says take a midpoint of each subinterval. And so this is the first subinterval at that midpoint, second subinterval at that midpoint, third subinterval at that midpoint, fourth subinterval at that midpoint, and fifth subinterval at that midpoint. Now, if the midpoint of 0 to 0.2 is 0.1, the midpoint 0.2 to 0.4 is 0.3, the midpoint 0.3 to 0.6 is 0.5, the midpoint 0.6, 0.8 is 0.7, midpoint 0.8, 0.9. I mean 0.8 and 1 is 0.9. So those are the midpoints of those 5 subintervals. It's just the average of the endpoint values, right? Okay, and so now to approximate, this is our function f of x. So f of x is the square root of 1 plus x cubed. This is approximately f of 0.1 times the length of that subinterval, which is 0.2, plus f of 0.3 times the length of the subinterval, which is 0.2, plus f of 0.5 times the length of the subinterval, 0.2, plus f of 0.7 times the length of the subinterval, 0.2, plus f of 0.9 times the length of the subinterval, which is 0.2. All right, and so that's equal to is f of 0.1, which is 1 plus 0.1 cubed, which is the square root of 1 plus 0.1 cubed, times 0.2, plus the square root of 1 plus 0.3 cubed, times 0.2, plus the square root of 1 plus 0.5 cubed, times 0.2. plus the square root of 1 plus 0.7 cubed times 0.2 plus the square root of 1 plus 0.9 cubed times the square root of times 0.2. All right, and then just add those 5 products and you get an approximation. Okay, just plug in your calculator. All right. Okay, so you plug in your calculator those 5 products, you add up those 5 products, and you get an approximation. So that's 35, using the midpoint rule with n equals 5. Okay, let's continue. Okay. Good. Okay, so then next one is number 40. Let's go over number 40. I want to do number 40 next. So for number 40, it says find the average value of the function f of x. This is a typo. Okay, the book has a typo here. It's f of t is equal to t sine of t squared. So that should be a t. Okay, on the interval (0, 2). Okay. Okay, so let's find the average value of that function on the interval from 0 to 2. Okay, so f average is equal to 1 over 2 minus 0 times def interval from 0 to 2 of f of t dt, or writing in f of t sine of t squared dt. Okay, so this is 1/2. Now, so this is making the t squared and the sine. This is weird. Let's make u equal to t squared. Du is going to be 2t dt. And so we're missing a 2. We have the t dt, but we're missing a 2. So we're going to put a 2 there. And so we have 1/2 from that. And we have our def interval from 0 to 2 of sine of t squared, and then a t dt. And we're missing a 2, so I'm going to put a 2 there, and then I'm going to put a 1/2 here. So this 1/2 is from here. We need another 1/2 to cancel that 2, right? And so then that's equal to 1/4 the integral sine of t squared, which is sine of u, 2t dt, which is du. And so when t is 0, u is 0. And when t is 2, u is 4. U is t squared. So when t is 2, u is 2 squared, which is 4. Okay. And so now, what's an antiderivative of sine of u? It's negative cosine u, evaluated from 0 to 4. And there's a 1/4 in front, so this is negative 1/4 cosine of u. And so this is equal to negative 1/4 times cosine of 4 minus cosine of 0. Okay, so cosine of 4 is just number. Cosine of 0 is 1, so this is 1. And so we get negative 1/4 times cosine of 4 minus 1. And you could reverse the signs and say this is 1/4 times 1 minus cosine of 4. And then that's the answer. All right, so 1/4 times 1 minus cosine of 4. It's a 4. All right, and so then that's the final answer for number 40. All right. Okay, good. So we have that. Let's do another one. So looking at the review problems at the end of this chapter, there are 44 problems. Let's do the last one. Let's do number 44. Okay, so number 44, evaluate. So number 44 is evaluate. It says the limit as n approaches infinity of 1 over n, so 1 over n to the 9th power, plus 2 over n to the 9th power, plus dot dot dot, plus n over n to the 9th power. Okay, I left out the 3 over n, it's the same. It's plus dot dot dot, includes the 3 over n to the 9th. Okay, so let's find this limit. So this is equal to the limit as n approaches infinity of 1 over n. Now I'm going to factor out a 1 over n to the 9th power every term. So I'm going to factor out 1 over n to the 9th power. And if I factor that out, Mark is now running out of ink as we approach the end of this video. Okay, so this is, I factor out the 1 over n to the 9th power. And so if you factor this out, if you factor out 1 over n to the 9th power, which is in every term, you're left with just the numerators, which is 1 to the 9th, plus 2 to the 9th, plus dot dot dot, plus n to the 9th. And so now we have the sum of 9th powers. Okay? So now we have the sum of 9th powers. Okay, so what is the sum of 9th powers? So what we need is a formula for the sum of 9th powers to plug in there and then multiply that out by. You will not need to know the sum of 9th powers for the exam. So I'm wondering if we should just not worry about it. Okay, so we don't have to worry about it. You plug in a formula here, and you get the sum of 9th powers. Let me know. I'll be right back. All right, I found it. Sorry about that. Wait. Okay, so I have the sum of 9th powers here. So the sum from k equals 1 to n of k to the 9th power, which is that sum, is equal to 1 over 20 times 2n to the 10th power plus 10n to the 9th power plus 15n to the 8th power minus 14n to the 6th power plus 10n to the 4th power minus 3n squared. Okay, so let me just make sure I got that right. Okay, so that is the sum formula. So this sum is that. So I'm going to substitute. So this is equal to the limit as n approaches infinity of 1 over n times 1 over n to the 9th, which is 1 over n to the 10th power, times that, which is 1 over 20 times 2n to the 10th plus 10n to the 9th plus 15n to the 8th minus 14n to the 6th plus 10n to the 4th minus 3n squared. Okay, and now if you divide by n to the 10th power, then if you divide this whole thing by n to the 10th power, this is equal to the limit as n approaches infinity of 1 over 20. I'm going to move the 1 over 20 out. And then this is going to be divided by n to the 10th power. So 2 times n to the 10th power divided by n to the power is 2. Plus, you have 10 over n. 10 to the 9th over n to the 10th is over n. Plus 15 over n squared. Minus 14 over n to the 4th. Plus 10 over n to the 6th. Minus 3 over n to the 8th. That's equal to, so if you take the limit as n approaches infinity, that goes to 0, that goes to 0, that goes to 0, that goes to 0, that goes to 0. So you get 1 over 20 times 2, which is 1 over 10. And the final answer is 1 over 10. That's the answer. Okay, so number 44 is 1 over 10. So that's the answer. Good. Okay. You do not need to know this formula for any exam. Okay, so just showing it to you here though. All right, let's continue. Okay, so so that was number 44. I'm happy with myself for getting that problem. Let's do this one, number 24. 24 is another indefinite integral, so this is the integral of sine x times cosine of cosine x dx. So this is weird. Okay, we're going to use substitution again. I'll pause for a moment so you can think about that to let u be in the problem. And so let's make u cosine x. So I'm going to let u equal cosine x to u equals negative sine x dx. Okay, so this is equal to the integral of cosine x. And then the negative goes there, so negative 1 sine x dx. Put negative there and the negative there, and the cancel, and you get a 1. And so this is equal to negative integral of cosine of, well, cosine x is u, and then negative sine x dx is du. And so now you have integral of cosine u du, negative. And so this is equal to negative sine of u plus c. Okay, and so we get that. And so now this is equal to negative sine of, and I'll just plug in for u cosine x. And you get that. Okay, so the integral of sine x times cosine of cosine x dx is negative sine of cosine x plus c. So that's the answer to number 24. Awesome. All right. Okay, so the video is good. Yeah, so we've done a lot of the problems here now. Okay, let's do another one. So let's do another integral. Okay, so let's do It's number 13. Okay, so number 13, make sure I didn't look at the same problem again. Okay, so number 13 is a definite integral from 0 to 1 of y times y squared plus 1 to the 5th dy. So this is equal to, let u equal y squared plus 1. Du is 2y dy. So now this is equal to the integral, well, of y squared plus 1 to the 5th. Now the y dy is there, and then you're missing a 2. So I'm just going to put a 2 there. I'm going to put a 2 there, and I'll multiply the outside by 1/2. Now I still have the integral from 0 to 1. So now this is equal to 1/2 the integral u to the 5th. 2y dy is du. When y is 0, u is 1. When y is 1, u is 2. That's moving the 0. That's definitely from 1 to 2. Okay? This is now 1/2 times the antiderivative u to the 5th is u to the 6th over 6 evaluated from 1 to 2. So this is, I'm going to move this, the denominator 6 is 1/2 times 1/6, which is 1/12 times 2 to the 6th minus 1 to the 6th. So you have 64 minus 1, which is 63. So you have 63 over 12. Okay? And so this is 5 and a fourth. So this is 5.25 as a decimal. All right, so now that definite integral is equal to 5.25. Okay, so that's number 13. Let's do another one. Still, I think we have time for one more. Okay, so let's do number 23. Okay, so for number 23, we find the integral of sine pi t cosine pi t dt. Okay, I mean, you could use u substitution twice. Let's say u equal pi t, and then you plug in for u, and then you let w be equal to cosine of u. Let's skip all that, and let's let u equal to sine of pi t. If we let u equal sine of pi t, du is equal to cosine of pi t times the derivative of pi t, which is pi. And so du is pi cosine pi t dt. Okay, so if we're going to use u substitution, we have the sine of pi t here. And cosine pi t dt is here, but we're missing a pi. So I'm going to put the pi there, and pi cosine pi t dt. And if I multiply by pi here, you multiply by 1 over pi there. Okay? And so now this is equal to 1 over pi, the integral of, well, sine of pi t is u. So there's u. And then pi cosine pi t dt, pi cosine pi t dt is du. And so that's u du. So this is 1 over pi integral u du, which is 1 over pi u squared over 2 plus c. This is equal to 1 over 2 pi times u squared. That's u. So it's sine squared pi t plus c. And so the final answer is the integral of that is 1 over 2 pi times sine squared of pi t plus c. Using u substitution, where u is sine of pi t. Okay, so we've now gone over the sections in 3.7 and chapter 4, and a lot of review problems at the end of the chapter. And so I hope that helps you see all the material we covered a little bit easier, and helps you calculate definite integrals and indefinite integrals, and do some more problems, be able to do more problems. Okay, so see you next time. Bye.